A core aspect of software engineering is the subdivision of the development process into a series of phases or steps, each of which focuses on one aspect of the development. The collection of these steps is sometimes referred to as the Software Development Lifecycle or SDLC. The software product moves through this lifecycle, sometimes repeatedly as it is refined or redeveloped, until it is finally retired from use. Ideally, each phase in the life cycle can be checked for correctness before moving on to the next phase. Software Development Lifecycle Waterfall. Let us start with an overview of the waterfall model, such as you will find in most software engineering textbooks. This waterfall illustrates a general waterfall model that could apply to any computer system development. It shows the process as a strict sequence of steps where the output of one step is the input to the next, and all of one step has to be completed before moving on to the next. We can use the waterfall process as a means of identifying the tasks that are required, together with the input and output for each activity. What is important is the scope of the activities, which can be summarized as follows. Establishing requirements involves consultation with and agreement among stakeholders about what they want from a system, expressed as a statement of requirements. Analysis starts by considering the statement of requirements and finishes by producing a system specification. The specification is a formal representation of what a system should do, expressed in terms that are independent of how it may be realized. Design begins with a system specification, produces design documents, and provides a detailed description of how a system should be constructed. Implementation is the construction of a computer system according to a given design document, and taking into account the environment in which the system will be operating. Example, specific hardware or software available for the development. Implementation may be staged, usually with an initial system that can be validated and tested before a final system is released for use. Testing compares the implemented system against the design documents and requirements specification and produces an acceptance report, or more usually a list of errors and bugs that require a review of the analysis, design, and implementation processes to correct. Testing is usually the task that leads to the waterfall model iterating through the life cycle. Maintenance involves dealing with changes in the requirements or the implementation environment, bug fixing, or porting of the system to new environments. Example, migrating a system from a standalone PC to a Unix workstation or a networked environment. Since maintenance involves the analysis of the changes required, design of a solution, implementation and testing of that solution over the lifetime of a maintained software system, the waterfall lifecycle will be repeatedly revisited. Database lifecycle. We can use the waterfall cycle as the basis for a model of database development that incorporates three assumptions. We can separate the development of a database, that is, specification and creation of a schema to define data in a database, from the user processes that make use of the database. We can use the three schema architecture as a basis for distinguishing the activities associated with a schema. We can represent the constraints to enforce the semantics of the data once within a database, rather than within every user process that uses the data. The first step is requirements gathering. During this step, the database designers have to interview the customers or database users to understand the proposed system and obtain, including documenting the data and functional requirements. The result of this step is a document that includes the detailed requirements provided by the users. Establishing requirements involves consultation with and agreement among all the users as to what persistent data they want to store, along with an agreement as to the meaning and interpretation of the data elements. The data administrator plays a key role in this process, as they overview the business, legal, and ethical issues within the organization that impact on the data requirements. The data requirements document is used to confirm the understanding of requirements with users, to make sure that it is easily understood. It should not be overly formal or highly encoded. The document should give a concise summary of all users' requirements, not just a collection of individuals' requirements, as the intention is to develop a single shared database. The requirements should not describe how the data is to be processed, but rather what the data items are, what attributes they have, what constraints apply, and the relationships that hold between the data items. Analysis. Data analysis begins with the statement of data requirements and then produces a conceptual data model. The aim of analysis is to obtain a detailed description of the data that will suit user requirements so that both high and low-level properties of data and their use are dealt with. These include properties such as the possible range of values that can be permitted for attributes. Example, in the school database example, the student course code, course title, and credit points. The conceptual data model provides a shared, formal representation of what is being communicated between clients and developers during database development. It is focused on the data in a database, irrespective of the eventual use of that data in user processes or implementation of the data in specific computer environments. Therefore, a conceptual data model is concerned with the meaning and structure of data, but not with the details affecting how they are implemented. The conceptual data model, then, is a formal representation of what data a database should contain and the constraints the data must satisfy. This should be expressed in terms that are independent of how the model may be implemented. As a result, analysis focuses on the questions: what is required, not how is it achieved. Logical design. Database design starts with a conceptual data model and produces a specification of a logical schema. This will determine the specific type of database system, network, relational, object-oriented, that is required. The relational representation is still independent of any specific DBMS. It is another conceptual data model. We can use a relational representation of the conceptual data model as input to the logical design process. The output of this stage is a detailed relational specification, the logical schema, of all the tables and constraints needed to satisfy the description of the data in the conceptual data model. It is during this design activity that choices are made as to which tables are most appropriate for representing the data in a database. These choices must take into account various design criteria, including, for example, flexibility for change, control of duplication, and how best to represent the constraints. It is the tables defined by the logical schema that determine what data are stored and how they may be manipulated in the database. Database designers familiar with relational databases and SQL might be tempted to go directly to implementation after they have produced a conceptual data model. However, such a direct transformation of the relational representation to SQL tables does not necessarily result in a database that has all the desirable properties: completeness, integrity, flexibility, efficiency, and usability. A good conceptual data model is an essential first step towards a database with these properties, but that does not mean that the direct transformation to SQL tables automatically produces a good database. This first step will accurately represent the tables and constraints needed to satisfy the conceptual data model description and so will satisfy the completeness and integrity requirements. But it may be inflexible or offer poor usability. The first design is then flexed to improve the quality of the database design. Flexing is a term that is intended to capture the simultaneous ideas of bending something for a different purpose and weakening aspects of it as it is bent. Realizing the design. After the logical design has been created, we need our database to be created according to the definitions we have produced. For an implementation with a relational DBMS, this will probably involve the use of SQL to create tables and constraints that satisfy the logical schema description and the choice of appropriate storage schema, if the DBMS permits that level of control. One way to achieve this is to write the appropriate SQL DDL statements into a file that can be executed by a DBMS, so that there is an independent record, a text file of the SQL statements defining the database. Another method is to work interactively using a database tool like SQL Server Management Studio or Microsoft Access. Whatever mechanism is used to implement the logical schema, the result is that a database with tables and constraints is defined but will contain no data for the user processes. Populating the database. After a database has been created, there are two ways of populating the tables, either from existing data or through the use of the user applications developed for the database. For some tables, there may be existing data from another database or data files. For example, in establishing a database for a hospital, you would expect that there are already some records of all the staff that have to be included in the database. Data might also be brought in from an outside agency. Address lists are frequently brought in from external companies, or produced during a large data entry task, like converting hard copy manual records into computer files can be done by a data entry agency. In such situations, the simplest approach to populate the database is to use the import and export facilities found in the DBMS. Facilities to import and export data in various standard formats are usually available. These functions are also known in some systems as loading and unloading data. Importing enables a file of data to be copied directly into a table. When data are held in a file format that is not appropriate for using the import function, then it is necessary to prepare an application program that reads in the old data, transforms them as necessary, and then inserts them into the database using SQL code specifically produced for that purpose. The transfer of large quantities of existing data into a database is referred to as a bulk load. Bulk loading of data may involve very large quantities of data being loaded, one table at a time, so you may find that there are DBMS facilities to postpone constraint checking until the end of the bulk loading. Guidelines for developing an ER diagram. Note, these are general guidelines that will assist in developing a strong basis for the actual database design, or the logical model. Document all entities discovered during the information gathering stage. Document all attributes that belong to each entity. Select a candidate and primary keys. Ensure that all non-key attributes for each entity are functionally dependent on the primary key. Develop an initial ER diagram and review it with appropriate personnel. Remember that this is an iterative process. Create new entities, tables, for multi-valued attributes and repeating groups. Incorporate these new entities, tables, in the ER diagram. Review with appropriate personnel. Verify ER modeling by normalizing tables. The entity relationship, or ER data model, has existed for over 35 years. It is well suited to data modeling for use with databases because it is fairly abstract and is easy to discuss and explain. ER models are readily translated to relations. ER models, also called an ER schema, represented by ER diagrams. ER modeling is based on two concepts: entities, defined as tables that hold specific information, data; relationships, defined as the associations or interactions between entities. Here's an example of how these two concepts might be combined in an ER data model. Professor Ba, entity, teaches, relationship, the database systems course, entity. For the rest of this chapter, we will use a sample database called the company database to illustrate the concepts of the ER model. This database contains information about employees, departments, and projects. Important points to note include: there are several departments in the company. Each department has a unique identification, a name, location of the office, and a particular employee who manages the department. A department controls a number of projects, each of which has a unique name, a unique number, and a budget. Each employee has a name, identification number, address, salary, and birth date. An employee is assigned to one department, but can join in several projects. We need to record the start date of the employee in each project. We also need to know the direct supervisor of each employee. We want to keep track of the dependents for each employee. Each dependent has a name, birth date, and relationship with the employee. Entity, entity set, and entity type. An entity is an object in the real world with an independent existence that can be differentiated from other objects. An entity might be an object with physical existence, example, a lecturer, a student, a car, or an object with conceptual existence, example, a course, a job, a position. Entities can be classified based on their strength. An entity is considered weak if its tables are existence dependent. That is, it cannot exist without the relationship with another entity. Its primary key is derived from the primary key of the parent entity. The spouse table in the company database is a weak entity because its primary key is dependent on the employee table. Without a corresponding employee record, the spouse record would not exist. An entity is considered strong if it can exist apart from all of its related entities. Kernels are strong entities. A table without a foreign key or a table that contains a foreign key that can contain nulls is a strong entity. Another term to know is entity type, which defines a collection of similar entities. An entity set is a collection of entities of an entity type at a particular point of time. In an entity relationship diagram, or ERD, an entity type is represented by a name in a box. Existence dependency. An entity's existence is dependent on the existence of the related entity. It is existence dependent if it has a mandatory foreign key, that is, a foreign key attribute that cannot be null. For example, in the company database, a spouse entity is existence dependent on the employee entity. Kinds of entities. You should also be familiar with different kinds of entities, including independent entities, dependent entities, and characteristic entities. These are described as follows. Independent entities, also referred to as kernels, are the backbone of the database. They are what other tables are based on. Kernels have the following characteristics. They are the building blocks of a database. The primary key may be simple or composite. The primary key is not a foreign key. They do not depend on another entity for their existence. Dependent entities, also referred to as derived entities, depend on other tables for their meaning. These entities have the following characteristics. Dependent entities are used to connect two kernels together. They are said to be existence dependent on two or more tables. Many relationships become associative tables with at least 2 foreign keys. They may contain other attributes. The foreign key identifies each associated table. There are 3 options for the primary key. Use a composite of foreign keys of associated tables if unique. Use a composite of foreign keys and a qualifying column. Create a new simple primary key. Characteristic entities provide more information about another table. These entities have the following characteristics. They represent multi-valued attributes. They describe other entities. They typically have a one-to-many relationship. The foreign key is used to further identify the characterized table. Options for primary key are as follows. Use a composite of foreign key plus a qualifying column. Create a new simple primary key. In the company database, these might include employee, like EID, name, address, age, salary. EID is the simple primary key. Employee phone, EID phone. EID is part of a composite primary key. Here, EID is also a foreign key. Attributes. Each entity is described by a set of attributes. Example, employee equals name, address, birth date, age, salary. Each attribute has a name and is associated with an entity and a domain of legal values. However, the information about attribute domain is not presented on the ERD. Types of keys. There are several types of keys. These are described as follows. Candidate key. A candidate key is a simple or composite key that is unique and minimal. It is unique because no 2 rows in a table may have the same value at any time. It is minimal because every column is necessary in order to attain uniqueness. From our company database example, if the entity is employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Possible candidate keys are EID, SIN, first name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming 2 people with the same last name don't work in the same department. Composite key. A composite key is composed of 2 or more attributes, but it must be minimal. Using the example from the candidate key section, possible composite keys are first name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming 2 people with the same last name don't work in the same department. Primary key. The primary key is a candidate key that is selected by the database designer to be used as an identifying mechanism for the whole entity set. It must uniquely identify tuples in a table and not be null. The primary key is indicated in the ER model by underlining the attribute. A candidate key is selected by the designer to uniquely identify tuples in a table. It must not be null. A key is chosen by the database designer to be used as an identifying mechanism for the whole entity set. This is referred to as the primary key. This key is indicated by underlining the attribute in the ER model. In the following example, EID is the primary key. Employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Secondary key. A secondary key is an attribute used strictly for retrieval purposes. Can be composite. For example, phone and last name. Alternate key. Alternate keys are all candidate keys not chosen as the primary key. Foreign key. A foreign key, or FK, is an attribute in a table that references the primary key in another table, or it can be null. Both foreign and primary keys must be of the same data type. Employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Nulls. A null is a special symbol independent of data type, which means either unknown or inapplicable. It does not mean zero or blank. Features of null include no data entry, not permitted in the primary key, should be avoided in other attributes, can represent an unknown attribute value, a known but missing attribute value, a not applicable condition. Can create problems when functions such as count, average, and sum are used. Can create logical problems when relational tables are linked. Note, the result of a comparison operation is null when either argument is null. The result of an arithmetic operation is null when either argument is null, except functions that ignore nulls. Normalization should be part of the database design process. However, it is difficult to separate the normalization process from the ER modeling process, so the two techniques should be used concurrently. Use an entity relation diagram, or ERD, to provide the big picture or macro view of an organization's data requirements and operations. This is created through an iterative process that involves identifying relevant entities, their attributes, and their relationships. Normalization procedure focuses on characteristics of specific entities and represents the micro view of entities within the ERD. So, what is normalization? Normalization is the branch of relational theory that provides design insights. It is the process of determining how much redundancy exists in a table. The goals of normalization are to be able to characterize the level of redundancy in a relational schema and provide mechanisms for transforming schemas in order to remove redundancy. Normalization theory draws heavily on the theory of functional dependencies. Normalization theory defines 6 normal forms, or NF. Each normal form involves a set of dependency properties that a schema must satisfy, and each normal form gives guarantees about the presence and/or absence of update anomalies. This means that higher normal forms have less redundancy, and as a result, fewer update problems. Normal forms. All the tables in any database can be in one of the normal forms we will discuss next. Ideally, we only want minimal redundancy for PK to FK. Everything else should be derived from other tables. There are 6 normal forms, but we will only look at the first 4, which are first normal form, or 1NF, second normal form, or 2NF, third normal form, or 3NF, Boyce Codd normal form, or BCNF. BCNF is rarely used. In the first normal form, only single values are permitted at the intersection of each row and column, hence there are no repeating groups. To normalize a relation that contains a repeating group, remove the repeating group and form 2 new relations. The PK of the new relation is a combination of the PK of the original relation, plus an attribute from the newly created relation for unique identification. Process for 1NF. We will use the student grade report table as follows from a school database as our example to explain the process for 1NF. Student grade report. Student number, student name, major, course number, course name, instructor number, instructor name, instructor location, grade. In the student grade report table, the repeating group is the course information. A student can take many courses. Remove the repeating group. In this case, it's the course information for each student. Identify the PK for your new table. The PK must uniquely identify the attribute value, student number, and course number. After removing all the attributes related to the course and student, you are left with the student course table, student course. The student table, student, is now in first normal form with the repeating group removed. Student, student number, student name, major. Student course, student number, course name, instructor number, instructor name, instructor location, grade. How to update 1NF anomalies. Student course, student number, course name, instructor number, instructor name, instructor location, grade. To add a new course, we need a student. When course information needs to be updated, we may have inconsistencies. To delete a student, we might also delete critical information about a course. Second normal form, 2NF. For the second normal form, the relation must first be in 1NF. The relation is automatically in 2NF if and only if the pk comprises a single attribute. If the relation has a composite pk, then each non-key attribute must be fully dependent on the entire pk and not on a subset of the pk. That is, there must be no partial dependency or augmentation. Process for 2NF. To move 2NF, a table must first be in 1NF. The student table is already in 2NF because it has a single column pk. When examining the student course table, we see that not all the attributes are fully dependent on the pk, specifically all course information. The only attribute that is fully dependent is grade. Identify the new table that contains the course information. Identify the pk for the new table. Student, student number, student name, major. Course grade, student number, course number, grade. Course instructor, course number, course name, instructor number, instructor name, instructor location. How to update 2NF anomalies. When adding a new instructor, we need a course. Updating course information could lead to inconsistencies for instructor information. Deleting a course may also delete instructor information. Third normal form, 3NF. To be in third normal form, the relation must be in second normal form. Also, all transitive dependencies must be removed. A non-key attribute may not be functionally dependent on another non-key attribute. Process for 3NF. Eliminate all dependent attributes in transitive relationships from each of the tables that have a transitive relationship. Create new tables with removed dependency. Check new tables as well as tables modified to make sure that each table has a determinant and that no table contains inappropriate dependencies. See the four new tables as follows: student, student number, student name, major. Course grade, student number, grade. Course, course number, course name, instructor number. Instructor, instructor number, instructor name, instructor location. Normalization and database design. During the normalization process of database design, make sure that proposed entities meet required normal form before table structures are created. Many real-world databases have been improperly designed or burdened with anomalies if improperly modified during the course of time. You may be asked to redesign and modify existing databases. This can be a large undertaking if the tables are not properly normalized. One important theory developed for the entity relational model involves the notion of functional dependency, or FD. The aim of studying this is to improve your understanding of relationships among data and to gain enough formalism to assist with practical database design. Like constraints, FDs are drawn from the semantics of the application domain. Essentially, functional dependencies describe how individual attributes are related. FDs are a kind of constraint among attributes within a relation and contribute to a good relational schema design. In this chapter, we will look at the basic theory and definition of functional dependency, the methodology for improving schema designs, also called normalization, relational design and redundancy. Generally, a good relational database design must capture all of the necessary attributes and associations. The design should do this with a minimal amount of stored information and no redundant data. In database design, redundancy is generally undesirable because it causes problems maintaining consistency after updates. However, redundancy can sometimes lead to performance improvements. For example, when redundancy can be used in place of a join to connect data. A join is used when you need to obtain information based on two related tables.